This video is going to talk about sets of two or more vectors, and we're going to start with Theorem 7. So one of the things that is true about linearly dependent sets is two or more vectors are linearly dependent in this set of vectors if and only if at least one of those vectors is a linear combination of the others. So it's linearly dependent if for some vector in there, okay, it is a linear combination of any of the preceding vectors. It doesn't have to be all of them, but just some of them. So if you ended up finding out that V3 was equal to 3 times V2, okay, then you would end up having a linearly dependent set of vectors between V1, V2, and V3, because V3 is linearly dependent on V2. It's a multiple of it. So let's look at this example. We're going to do a little bit of a proof explanation on this one. So we have U and V, and the first thing I want to check is the relationship between U and V. So is V equal to something times a scalar times U? 1/3 to get 3 to 1 is not the same as that. No, so that is not the case. So notice that U and V are linearly independent. Okay, we're having if and if situation. So in order to do this, we have to kind of show both sides. So we assume one side and then show the other has to be true, and then vice versa. So if W is in the span of UV, then we say that W must be equal to some constant times U plus some constant times V. Well, if that's the case, then it's dependent on U and V, so W depends on U and V, which makes it a linear dependent set, because W depends on U and V. I know U and V don't depend on each other, but W depends on U and V, so that set is a linearly dependent set. Well, if it's also the case that U and V and W are a linearly dependent set, then they must be a linear combination of each other. Well, we know these things are true. So if the set U, V, W linearly dependent, and it's not U and V, then W must be equal to a linear combination of U and V. Well, then it's in the span, is what we say. Okay, so there's a little proof for example 1. Let's look at another theorem in our book. So if a set contains more vectors than there are entries in each vector, then there has to be linear dependence. So if P is greater than N in that little diagram, then there has to be a linear combination going on. Think about it, your pivot columns, or your pivot rows, sorry, you're not going to have a pivot row in each one of your rows, or pivot in each one of your rows. So this violates a lot of that theorem 4 that we talked about, okay? So let's look at example 2, and it's just written out here. We don't really need to write a whole lot. It's just a little snippet from the book. So if we have these vectors that are in R2, because there are 3 vectors in the set, like if I were to make this into a matrix, okay, then they are going to end up being linearly dependent because there are more vectors than rows. So there's going to end up being a way to write one of those vectors in terms of the other. All right, if a set contains the 0 vector, then the set must be linearly dependent. If that set contains a 0 vector, then they must be linearly dependent. So let's look at this, and just by inspection, let's figure this out if the set is linearly dependent. Well, in this one, if I make this one big matrix, I have more columns than rows dependent. Here, I have a 0 vector dependent. C, I'm noticing, okay, I have more rows than columns, but is V a scalar times U? And if you look, it does look like if I break this down, one thing I also like to think about is like, or is U and V, is VU a different multiple of the same like base vector? Maybe we'd call it X. And if I divide everything here by -2, I get 1, -2, -3, 5, -5. If I divide everything in this other vector by 3, I get 1, -2, -3, +5. So those don't end up being the exact same vector. So therefore, there isn't like this down here, doesn't happen. They don't have that same base vector. So this is not true. There isn't going to end up being some multiple. I thought maybe it would be, you know, like we could take 2 times like 3, -3 halves. And it does do this, this, and this, but these have the same sign, right? So these are actually linearly independent.